In this video, we're going to talk about three main points. First, we'll talk about when to use a z for a sample mean versus a one sample t-test. Then we'll discuss when to use a one-tailed test versus a two-tailed hypothesis test. And finally, we'll do a full example of a one sample t-test. So the choice between using a one sample t-test versus a z for a sample mean is pretty straightforward. In this situation, we have a population with known parameters of 50 and 4. Of course, we can't study the entire population, so we take a sample of 25. We treat the entire sample, and the question is, what's the mean of the sample after treatment? And like before, what we're trying to decide is any variation between this sample mean and this population mean. What's the most likely cause of that variation? Is it sampling error, or is it the treatment having an effect? Well, in this situation, we know the population standard deviation is 4, so we would use a z for a sample mean. When you know the population standard deviation, you use the z for a sample mean. If this question were changed such that you do not know the population standard deviation, then you would have to use a one sample t-test. And what you would do instead of using the standard deviation of the population is you would compute the standard deviation of the sample. From these 25 people, you would find their standard deviation, and you would just use that instead of the population standard deviation. It's really that simple. Now we're going to talk about when to use a one-tailed test versus a two-tailed test. I've drawn a distribution of sample means here with the z-score number line under it. In this first situation, researchers expect the IV to increase scores. An example might be they want to test to see if a drug is going to increase people's memory scores. Now, obviously, if the drug is meant to increase memory scores, they're not going to be interested in using it if it actually hurts memory. They're only interested in using this IV if it actually increases people's scores. In this situation, we're going to use a one-tailed test, and that simply means that we're going to have one critical region on this side. And so we'll find the critical value, and that will be determined by alpha of alpha 0.05. We'll look up the critical value in the back of the book. We'll find what the critical value is. And if we get something in this critical region, we'll reject the null. This is 5%. This area is 5% of the entire curve. And again, in this situation, because the IV is intended to increase scores, or there's an expectation that the IV will increase scores, we're going to use a one-tailed test. Here's a different situation. Researchers now expect that the IV will decrease scores. An example of this might be that they have a drug for cholesterol. And obviously, if the drug works, they would expect that to lower cholesterol. Or maybe a drug that treats depression. They would, if it works, you'd expect depression scores to go down. In this situation, again, you're going to use a one-tailed test, except now the tail is going to be on the negative side, because you expect scores to go down if it works. So we'll find the critical value again, and if we get something in this region, we'll reject the null. But these are both one-tailed tests. You'll look up the critical value in the back, and of course, you'll just have to know that it's negative because of the context, because you expect scores to go down. In this last scenario, we're going to be using a two-tailed test, and that's when researchers do not have an expectation. To keep with the drugs example, maybe this time we've got a drug for depression, but we don't know what that's going to do to maybe weight gain. Maybe it'll have an adverse effect on people's weight. Maybe it'll cause them to gain weight. Maybe it'll cause them to lose weight. We don't know. It's a side effect, perhaps. In this situation, we're going to use a two-tailed test because we don't really have an expectation. We're looking to see, is it going to have any kind of effect? And so in this case, we're going to have a critical region on the top side and a critical region on the bottom side. Now, what makes this different is we still might have an alpha value equal to 0.05. But what that means, because we have a two-tailed test, is 2.5% of the curve is in this region, and 2.5% of the curve is in this region. So we're splitting that alpha into two regions. So we're going to have two critical values. They're going to be the same value, but one's going to be positive and one's going to be negative. And if we get something in this region, that means that the drug significantly increased people's weight. And if we get something in this region, that means the drug significantly decreased people's weight. Again, the critical point is whether or not you have an expectation of what the IV is supposed to do. In both of these situations, you're going to do a one-tailed test. In this situation, you're going to do a two-tailed test. Now finally, we're going to walk through a full example of a one-sample t-test. In this situation, researchers want to know if a curricular change will affect students' level of satisfaction with their college. Right now, their level of satisfaction on a standardized questionnaire is 12. The population mean satisfaction score is 12. That's mu. And the sample mean is 13.5. That's M. SD is the sample standard deviation. And N, of course, is the sample size. So those are all your givens. The first thing you want to do is state the null hypothesis and the research hypothesis. In this case, the null hypothesis can be written as the mean of the entire population, were we to put them all through the curricular change, would be equal to 12. That's the null. We're saying that the treatment isn't going to change people's satisfaction at all. So the mean after the treatment, if we were to treat the entire population, would still be 12. That's what the null is saying. The research hypothesis is saying something else. After the treatment, after experiencing the curricular change, the score is not going to be 12. It might be significantly higher than 12, it might be significantly lower than 12, but it's not going to be 12. It's going to change it in some way. The next step is to find the critical region. And you do that by determining or calculating the degrees of freedom. For a one-sample t-test, the degrees of freedom is the number of people in the study, in this case 25, minus 1. So we have a degrees of freedom of 24. Then we look up the critical values in the back of the book, in the appropriate appendix. If we look up 24 for a two-tailed hypothesis test, this is going to be two-tailed because, again, we don't have an expectation. We don't know if this curricular change is going to increase or decrease people's satisfaction. We have no expectation. So we're going to have two values. We go and look up 24 in the back of the book under two-tailed, and we'll find 2.0639. And now we know that it's two-tailed, so we're going to have a critical value on the negative side and the positive side at that value. And here's a picture that depicts that. So if we get something in this region or this region, we're going to reject the null. If we get something up here, we're going to say that the treatment increased people's satisfaction scores. And if we get something down here, we're going to say that it decreased satisfaction scores. The next thing to do is to compute the actual statistic. We're going to use the Z for a, or excuse me, we're going to use the the t-test formula. And I made a mistake there. That should be SD. And when we put those in, we compute 1.875 as the obtained T. That's a T, not a Z. And we locate that on the curve. It is not in the critical region, so we are not going to reject the null. The next thing we're going to do is compute the effect size. After we substitute in the values, we find that we have an effect size of 0.375, which is somewhere between small and medium-sized effect. The next thing to do is to compute, or excuse me, to summarize the results. And this is going to look a little long, but once we break it down into the parts, you'll see it's not that much different, or not that much more complicated than what we've already done. Those students experiencing the curricular change had a mean college satisfaction score that was not different from the population mean. And then I have a bunch of stat stuff in there. However, the effect size was close to medium in size, suggesting that the failure to reject the null may be the result of the sample size being too small. Further research should be done before firm conclusions are made. Period would be nice. Now notice I've written in that mu equals 12 here. My computer wouldn't put that symbol in easily, so I just wrote it in by hand. Again, I have a T here because I ran a t-test. This is the degrees of freedom in the parentheses. And this is the T score that I calculated. We actually calculated 1.875, and I just rounded to 2 decimals. We usually round to 2 decimals when you write up results. Because we did not reject the null, P is greater than 0.05, and then we wrote the D. So this first sentence is simply saying whether or not you rejected the null, really. Remember, you're trying to decide when you do a significance test whether the difference between the sample mean and the population mean is likely or unlikely to be due to sampling error. Well, in this case, it could have been done due to sampling error because the P was greater than 0.05. So that's simply what we're saying. The sample mean was not different from the population mean. That's what the first part says. And then we just add in all the statistical information at the end of the sentence. And then finally, because we have a D that's almost medium and we did not reject the null, that should suggest to you that maybe our significance test did not have sufficiently large sample size. We did not perhaps have enough statistical power. And so it's worth telling your readers that. Really what you should do is rerun the study with a larger sample size.